Hey everyone and welcome. Today we're diving into a topic that many students find tricky, but is absolutely essential in chemistry: stoichiometry and the mole concept. By the end of this video, I hope it finally makes sense. Don't worry if it's felt confusing in the past. We're going to break it down step by step, starting from the very basics and working our way up. You'll see how it all connects. First, we'll talk about the foundation of all these calculations, a concept known as the mole. The mole isn't some furry little animal. It's a unit that helps chemists count atoms, molecules, and other particles. Think of it like a chemist's dozen. Just as a dozen always means 12, a mole always means a specific number of particles. Then we'll tackle stoichiometry. This is the part where we use chemical equations to predict the amounts of substances involved in a reaction. It's the art of using balanced equations for calculations. It allows us to ask and answer questions like, if I have this much of chemical A, how much chemical B can I make? It might sound a bit intimidating, but it's all based on logical thinking and a few key conversions. Let's get started with our first topic, the mole. Let's begin with the mole concept. Our goal in this section is for you to be able to understand the definition of a mole and its numerical value, which is Avogadro's number. So what exactly is a mole? As I mentioned, it's a unit. Specifically, it's the amount of substance that contains as many particles as there are atoms in exactly 12 grams of the isotope carbon-12. That's a bit of a technical definition, so let's simplify it. Think of it like this. If you could zoom in and count individual atoms in a 12-gram sample of pure carbon-12, the number you'd get is 1 mole. It's just a gigantic number. That number is approximately 6.022 times 10 to the power of 23. This number is so important that it has its own name, Avogadro's number, represented by the symbol Na. Let's be clear about what we mean by particles. A particle can be an atom, like a hydrogen atom, a molecule, like a water molecule, or an ion, like a chloride ion. It can even be a formula unit for ionic compounds. So 1 mole of any of these substances will always contain 6.022 times 10 to the power of 23 particles of that substance. This is the core idea of the mole. It connects the microscopic world of atoms and molecules to the macroscopic world of grams and milliliters that we can measure in the lab. Now that we know the mole represents Avogadro's number of particles, our next objective is to be able to use Avogadro's number to convert between moles and the number of particles. The formula we'll use for these conversions is quite simple. The number of moles, which we'll call N, is equal to the number of particles, capital N, divided by Avogadro's number. Let's rewrite that to make the conversion factor clear. To find the number of moles from the number of particles, you divide by Avogadro's number. To find the number of particles from the number of moles, you multiply by Avogadro's number. Let's try our first worked example to see this in action. Suppose you're asked, how many particles are in 2.50 moles of glucose, C6H12O? First, identify what you're given. You have 2.50 moles of glucose, and you need to find the number of particles. Remember, the particles here are molecules, since glucose is a molecular compound. We use our formula. Number of particles equals moles times Avogadro's number. Now we substitute our values. 2.5 moles times 6.022 times 10 to the 23 molecules per mole. Notice how the mole units cancel out. When we do the math, we find that there are 1.51 times 10 to the 24 molecules in that 2.50 mole sample. So we've successfully converted moles to particles. Now let's go the other direction. For our second example, we'll convert from particles to moles. The question is, a sample contains 1.81 times 10 to the 4 formula units of sodium chloride, NaCl. How many moles is this? Again, we start by identifying what we know and what we need to find. We're given the number of particles, formula units in this case because NaCl is an ionic compound, and we need to find the number of moles. The formula is number of moles equals number of particles divided by Avogadro's number. Plugging in our numbers, We have 1.81 times 10 to the 4 formula units divided by Avogadro's number. Notice the formula units cancel. The result is 3.01 moles. So 1.81 times 10 to the 24 formula units of NaCl is equivalent to 3.01 moles of NaCl. See how the same principle applies, just in reverse. Let's try one more mole-to-particle conversion, this time with a diatomic element, to ensure we understand the term particles. Here's the question. How many atoms are in 1.25 moles of oxygen gas? Now, be careful here. What is the particle of oxygen gas? It's not a single atom. Oxygen gas exists as diatomic molecules, O2. So 1.25 moles of oxygen gas means 1.25 moles of O2 molecules. This problem has two steps. First, we'll find the number of O2 molecules, and then we'll use the chemical formula to find the total number of atoms. Step 1. Convert moles of O2 molecules to the number of O2 molecules. We multiply 1.25 moles by Avogadro's number. This gives us 7.53 times 10 to the 23 O2 molecules. Now for step 2. Look at the chemical formula, O2. Each molecule of oxygen gas contains 2 oxygen atoms. So we multiply our number of molecules by 2. This gives us 1.51 times 10 to the 24 atoms of oxygen. This two-step process is a key skill to master, so take a moment to understand why it was necessary. We had to account for the diatomic nature of the gas. Okay, it's your turn to practice. Here are 2 questions for you to work through. Pause the video and give them a try. First, how many molecules are in 0.75 moles of hydrogen gas, H2? Second, a vial contains 2.41 times 10 to the 22 atoms of iron, Fe. How many moles of iron are in the vial? All right, let's go over the solutions. For question 1, you should have multiplied the moles by Avogadro's number to get 4.5 times 10 to the 23 molecules of H2. For question 2, you divide the number of atoms by Avogadro's number, which gives you 0.0400 moles of Fe. This might seem like a small number, but it's still a significant amount of material that we can work with in the lab. Great job! You are now able to use Avogadro's number to convert between moles and particles. Let's move on to the next concept, molar mass. Our next objective is to define and calculate the molar mass of any substance using the periodic table. So what is molar mass? It's simply the mass, in grams, of 1 mole of a substance. In other words, it's the mass of 6.022 times 10 to the 23 particles of that substance. The units for molar mass are grams per mole, which we write as mol. This unit tells us the mass of each mole of a substance. The amazing thing is, you already know how to find it. You just need a periodic table. The atomic weight listed for each element on the periodic table, that number usually with decimal places, represents 2 things. The average mass of an atom of that element in atomic mass units, or AMU, and it's the molar mass of that element in grams per mole. So, to find the molar mass of a compound, you just add up the molar masses of all the atoms in its chemical formula. Let's work through some examples to solidify how to calculate molar mass. This is a critical skill for all stoichiometry problems. First example, what is the molar mass of water, H2O? The formula tells us we have 2 hydrogen atoms and 1 oxygen atom in each molecule. We find the atomic weights on the periodic table. Hydrogen is 1.01 grams per mole, and oxygen is 1,600 grams per mole. Now we add them up. It's 2 moles of hydrogen plus 1 mole of oxygen. So 2 times 1.01 plus 1,600 equals 18.02 grams per mole. That means 1 mole of water, which is Avogadro's number of water molecules, has a mass of 18.02 grams. Let's try a slightly more complex molecule to make sure the process is clear. Second example. What is the molar mass of lactic acid, CpH6O3? The formula tells us we have 3 carbon, 6 hydrogen, and 3 oxygen atoms. From the periodic table, the molar masses are approximately 12.01 for carbon, 1.01 for hydrogen, and 1,600 for oxygen. Now we calculate. We take 3 times the molar mass of carbon, plus 6 times the molar mass of hydrogen, plus 3 times the molar mass of oxygen. Adding those up gives us 36.03 plus 6.06 plus 4,800, for a grand total of 90.09 grams per mole of lactic acid. See, it's just adding the parts together. Finally, let's look at the molar mass of an ionic compound that contains a polyatomic ion, just to see how to handle those. Example 3. What is the molar mass of magnesium phosphate, Mg3PO42? The formula tells us we have 3 magnesium atoms. And because the polyatomic phosphate ion, PO4, is in parentheses with a 2 subscript, it means we have 2 of the entire PO4 group. So that's 2 phosphorus atoms and 8 oxygen atoms. To recap, we have 3 magnesium atoms, 2 phosphorus atoms, and 8 oxygen atoms. From the periodic table, magnesium is 24.31, phosphorus is 30.97, and oxygen is 1,600 grams per mole. So we calculate the total molar mass. 3 times the molar mass of magnesium, plus 2 times the molar mass of phosphorus, plus 8 times the molar mass of oxygen. This gives us 72.93 plus 61.94 plus 128 hundredths for a total of 262.87 grams per mole. Don't let the parentheses scare you. It's the same process. Time for more practice. Calculate the molar mass for these 2 substances. Remember to use the periodic table and show your work. Pause the video and give it a try. Question 1. What is the molar mass of sucrose, which is common table sugar with the formula C212H22O11? Question 2. What is the molar mass of ammonium sulfate, NH42SO4? All right, let's see how you did. For the sucrose, you should have calculated a molar mass of 342.34 grams per mole. That's 12 carbons, 22 hydrogens, and 11 oxygens. For the ammonium sulfate, you need to count the atoms carefully. There are 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens. The molar mass should be 132.1 grams per mole. I hope you got both of those. Mastering this calculation is so important. So, you are now able to calculate the molar mass of any substance. Let's combine what we've learned and start converting between moles and mass. Our next objective is to convert between moles and mass using the molar mass. This conversion is so frequent in chemistry, it has its own formula, often called the mole equation. The number of moles, N, is equal to the mass of the substance, lowercase m, divided by its molar mass, capital M. Just like before, we can rearrange this formula to solve for mass. Mass equals moles times molar mass. Let's work through an example. Suppose we have 3.50 moles of calcium chloride, CaCl2, and we want to find its mass. First, we need the molar mass of CaCl2. Calcium is 40.08, and we have 2 chlorine atoms, each 35.45. So the molar mass is 40.08 plus 2 times 35.45, which is 110.98 grams per mole. So we found the molar mass, 110.98 geosmol. Now we use our mole equation. Mass equals moles times molar mass. 350 moles times 110.98 grams per mole gives us 388 grams of calcium chloride. Notice how the mole units cancel, leaving us with grams, which is the unit for mass. Now let's go the other way, from mass to moles. Second example, how many moles are in a 50.0 gram sample of sodium bicarbonate, NaHCO3? Given Cm equals 50.0 grams of NaHCO3. Find N equals question mark. As always, the first step is to calculate the molar mass of NaHCO3. Sodium is 22.99, hydrogen is 1.01, carbon is 12.01, and we have 3 oxygens at 1,600 each. Adding those up, we get a molar mass of 84.01 grams per mole for baking soda. Now we use the mole equation, rearranged for moles. N equals m over m. So 50.0 grams divided by 84.01 grams per mole. The result is 0.595 moles of sodium bicarbonate. So a 50-gram sample contains about 0.6 of a mole. Okay, let's tie everything together. In our final worked example on mole conversions, we'll go from mass to moles to the number of atoms. This is a classic stoichiometry pathway. The question is, A piece of magnesium metal has a mass of 4.60 grams. How many atoms of magnesium are in the piece? Given m equal 4.6 find number of atoms. We can't count atoms directly from mass. The mole is the bridge. So, our first step is to convert the mass to moles. From the periodic table, the molar mass of magnesium is 24.31 grams per mole. Using the mole equation, moles equals 4.60 divided by 24.31, which is 0.189 moles of magnesium. Now that we have moles, we can use Avogadro's number to find the number of atoms. Remember, Avogadro's number converts moles to particles. Step 2 is to convert moles to atoms. We take our moles, 0.189, and multiply it by Avogadro's number. This gives us 1.14 times 10 to the 23 atoms of magnesium. This two-step process, mass to moles, then moles to particles, is a cornerstone of chemistry. If you understand this, you're in great shape for stoichiometry. Okay, let's practice the mole-to-mass conversions. These are the most common type of calculation you'll do in chemistry. Question 1. Calculate the mass in grams of 0.400 moles of copper-2 nitrate QNO3 Question 2. A sample of iron-3 chloride FeCl3 has a mass of 12.0 grams. How many moles are present? Take a moment to work these out. Ready for the answers? For question 1, you should have calculated the molar mass of copper-2 nitrate to be 187.56 g/mol, and then multiplied that by 0.400 moles to get 75.0 grams. So 0.400 moles of copper nitrate has a mass of 75.0 grams. For question 2, the molar mass of iron-3 chloride is 162.2 g/mol. Then you divide the mass by the molar mass. 12.0 grams divided by 162.20 grams per mole gives you 0.0739 moles. Great job if you got that. So a 12.0 gram sample of iron-3 chloride contains 0.0739 moles of the compound. At this point, you should be comfortable with all the mole concept conversions. Let's recap what we've covered. Let's quickly recap our mole concept conversions. We've seen how the mole is the central hub, allowing us to connect all these other quantities. The mole is our central unit. From the mole, we can convert to the number of particles using Avogadro's number. To get to mass, we use the molar mass. To get to particles, we use Avogadro's number. To go in the reverse direction, from mass to moles, you divide by the molar mass. And from particles to moles, you divide by Avogadro's number. You might notice an arrow pointing to volume, labeled 22.4 liters. This is another key conversion that applies only to gases at standard temperature and pressure, which we won't cover in this video, but it shows you that the mole is a universal connector. If you're ever stuck on a stoichiometry problem, ask yourself, how can I get to moles? Once you're in moles, you can get to anything. Now that we've mastered the mole concept, we can move on to stoichiometry. Our goal here is to use a balanced chemical equation to perform mole-to-mole calculations. So what is stoichiometry? It's the study of the quantitative relationships in chemical reactions. In other words, it's about doing math with chemical equations. Stoichiometry allows us to answer questions like, if I burn this much gasoline, how much carbon dioxide will be produced? Or, if I have this much of chemical A, what's the maximum amount of chemical B I can make? The recipe for stoichiometry is 4 simple steps, but they are crucial. Step 1. Always, always, always start with a balanced chemical equation. Without a balanced equation, you will get the wrong answer. The coefficients in the balanced equation, the numbers in front of each chemical, are your molar ratio recipe. Step 2. Identify what you're given and what you need to find. Step 3. Convert your given quantity to moles. Remember our mole island? This is how you start your journey. And step 4. Use the molar ratio from your balanced equation to convert the moles of your given substance into the moles of your desired substance. Let's see this in action. Let's work through our first stoichiometric calculation, a simple mole-to-mole problem. The question is, how many moles of oxygen gas, O2, are produced from the decomposition of 5.0 moles of potassium chlorate, KClO3? Step 1. We need a balanced equation. The decomposition of potassium chlorate produces solid potassium chloride, KCl, and oxygen gas, O2. After balancing, we get 2 KClO3 yields 2 KCl plus 3 O2. Step 2. We are given 5.0 moles of potassium chlorate, KClO3, and we need to find the moles of oxygen, O2. Step 3. The given amount is already in moles, so we can skip step 3. We're already on moles island. Step 4. Use the molar ratio. We look at our balanced equation. For every 2 moles of KClO3 that decompose, 3 moles of O2 are produced. We can write this as a conversion factor. 3 moles of O2 over 2 moles of KClO3. Finally, we set up our calculation. We take our 5.0 moles of KClO3 and multiply it by our molar ratio. The moles of KClO3 cancel out, and we are left with moles of O2. The answer is 7.5 moles of oxygen. So, decomposing 5 moles of potassium chlorate makes 7.5 moles of oxygen. Now let's step up the difficulty a notch with a mass-to-mole stoichiometry problem. The question is, if 40.0 grams of propane, C3H8, is completely burned in oxygen, how many moles of carbon dioxide, CO2, are produced? Step 1. Balance the equation for the combustion of propane. Propane plus oxygen yields carbon dioxide and water. The balanced equation is C3H8 plus 5O2 yields 3CO2 plus 4H2O. Step 2. Identify given and find. We are given 40.0 grams of propane, and we need to find the moles of carbon dioxide. Step 3. Our given propane is in grams. We need to convert it to moles. For this, we'll need propane's molar mass. The molar mass of propane is about 44.1 by-cos-mole, so 40.0 grams divided by 44.11 g-mol gives us 0.907 moles of propane. Step 4. The molar ratio from the balanced equation. For every 1 mole of propane, 3 moles of carbon dioxide are produced. We multiply our moles of propane by this ratio. The result is 2.72 moles of carbon dioxide. This problem required a calculation to get to moles and then a molar ratio to solve. It shows the power of the mole as an intermediate. Our final example in this section is the most comprehensive, a mass-to-mass stoichiometry problem. This is a very common type of calculation in chemistry. The question is, a synthesis reaction produces 20.0 grams of ammonia, NH3. What mass of nitrogen gas, N2, was needed for this reaction? Step 1. Balance the equation. The synthesis of ammonia from nitrogen gas and hydrogen gas is N2 plus 3H2 yields 2NH3. Step 2. We are given 20.0 grams of ammonia, NH3, and we need to find the grams of nitrogen, N2. This problem has 3 main steps: mass of A to moles of A, then moles of A to moles of B, and finally moles of B to mass of B. It's a 3-step journey across our mole island diagram. Step 3. Convert the given mass of ammonia to moles. The molar mass of ammonia is 17.04 grams per mole. Dividing the mass by the molar mass gives us 1.17 moles of ammonia. Step 4. Use the molar ratio to convert from moles of ammonia to moles of nitrogen. The balanced equation shows that for every 2 moles of NH3 produced, 1 mole of N2 is used. So we multiply our moles of ammonia by the ratio 1/2, which gives us 0.585 moles of nitrogen. Step 5. Convert the moles of nitrogen to its mass. The molar mass of diatomic nitrogen, N2, is 2 times 14.01, or 28.02 grams per mole. Multiplying our moles of N2 by its molar mass gives us 16.4 grams of nitrogen. So, to make 20.0 grams of ammonia, you would need to start with 16.4 grams of nitrogen. This mass-to-mass conversion is the most complete example of stoichiometry. If you can follow this logic, you understand the process. It's time for some more practice. I'll give you two problems. Pause the video and work them out using the stoichiometric recipe. Remember, start with a balanced equation. Question 1. The reaction of hydrochloric acid with calcium carbonate produces calcium chloride, water, and carbon dioxide. If 2.5 moles of HCl react, how many moles of carbon dioxide are formed? Question 2. If 15.0 grams of lithium hydroxide react with carbon dioxide, what mass of lithium carbonate is produced? Let's review the answers. For question 1, the balanced equation is 2HCl plus KCO3 goes to CaCl2 plus H2O plus CO2. The molar ratio of HCl to CO2 is 2 to 1. So 2.5 moles of HCl times 1 mole of CO2 over 2 moles of HCl gives 1.25 moles of carbon dioxide. The answer is 1.25 moles of carbon dioxide. For question 2, the balanced equation is 2 LiOH plus CO2 gives Li2CO3 plus H2O. This is a mass-to-mass problem. First, convert the 15 grams of LiOH to moles using its molar mass. That's 0.627 moles. Then use the molar ratio of 2 moles LiOH to 1 mole, Li2CO3 to get 0.3135 moles of lithium carbonate. Finally, convert that to mass using the molar mass of lithium carbonate, which is 73.89 grams per mole. Your final answer should be 23.2 grams of lithium carbonate. You are now able to perform stoichiometric calculations using a balanced equation. That's a huge milestone. Let's introduce one more important concept in stoichiometry: limiting reactants. Our objective here is to be able to identify the limiting and excess reactants in a chemical reaction. In many real-world reactions, you won't have the reactants in the exact molar ratio required by the balanced equation. You'll often have an excess of one reactant and a shortage of another. The reactant that runs out first is called the limiting reactant. It's the one that stops the reaction, just like a recipe. If you're making sandwiches and you have 20 slices of bread but only 4 slices of cheese, the cheese is your limiting reactant. You can only make 4 cheese sandwiches. The bread is in excess. The limiting reactant is the most important one. It's the one that determines the maximum possible amount of product you can make. This maximum amount is called the theoretical yield. So how do we identify the limiting reactant in a chemistry problem? There are a couple of ways. Let's try one. Here's our first example. Suppose we have 2 moles of hydrogen gas and 1 mole of oxygen gas. When they combine to form water, which is the limiting reactant? Step 1. We need a balanced equation. 2H2 plus O2 yields 2H2O. Step 2. We have 2 moles of H2 and 1 mole of O2. We need to find the limiting reactant. Here's the method. For each reactant, we'll calculate how many moles of a product it could theoretically make. The reactant that makes less product is the limiter. Let's assume all the hydrogen reacts. From the equation, the ratio of H2 to H2O is 2 to 2, so 2 moles of H2 would produce 2 moles of H2O. Now let's assume all the oxygen reacts. The ratio of O2 to H2O is 1 to 2, so 1 mole of O2 would produce 2 moles of H2O. In this specific case, both reactants produce the exact same amount of water. This is an ideal situation, called a stoichiometric mixture, where there is no limiting reactant. They will both run out at the same time. This was a setup problem, but it illustrates the idea. Okay, let's do an example where we actually have a limiting reactant. The question is, nitrogen gas reacts with hydrogen gas to produce ammonia. If you start with 28.0 grams of nitrogen and 5.0 grams of hydrogen, which is the limiting reactant? Step 1 is a balanced equation. N2 plus 3H2 yields 2NH3. Step 2. We have 28.0 grams of N2 and 5.0 grams of H2. We need to find the limiting reactant. Because our given amounts are in grams, the first thing we must do is convert them both to moles. Remember, stoichiometry is always done in moles. Step 3. We convert both reactants to moles. For nitrogen, 28.0 grams divided by its molar mass of 28.02 cutbasuk mole gives 1.07 moles of N2. For hydrogen, 5.0 grams divided by its molar mass of 2.02 g per mole gives 2.47 moles of H2. Now we compare the moles. We'll use our product method, calculating how much ammonia each reactant could make. Step 4. From the balanced equation, 1 mole of N2 can make 2 moles of NH3. So our 1 mole of N2 could make 2 moles of NH3. Next, let's see how much product the hydrogen could make. The ratio from the equation is 3 moles of H2 to 2 moles of NH3. So 2.47 moles of H2 would produce 1.65 moles of NH3. Now we compare the two results, 2 moles versus 1.65 moles. The smaller amount is the actual amount of product that can be formed. Since hydrogen produces less ammonia, it is the limiting reactant. It will run out first. This means that the maximum amount of ammonia we can make is 1.65 moles, and once we make that, we'll have hydrogen left over. The reactant in excess is nitrogen. There is a second, slightly quicker way to find the limiting reactant. Let's call it the molar ratio comparison method. Our third example will use this technique. The question is, if 4 moles of aluminum react with 3 moles of oxygen, which is the limiting reactant? Step 1. Balanced equation. 4Al plus 3O2 yields 2Al2O3. Step 2. We have 4 moles of Al and 3 moles of O2. Step 3. Let's find our theoretical molar ratio from the balanced equation. It tells us we need 4 moles of aluminum for every 3 moles of oxygen. So the theoretical molar ratio is 4/3, which equals 1.33. Step 4. Let's calculate the actual molar ratio of what we have. We have 4 moles of aluminum and 3 moles of oxygen, so the actual ratio is also 4/3, or 1.3. We compare the actual ratio to the theoretical ratio. What do you see? They are the same. Since the actual ratio equals the theoretical ratio, this is another stoichiometric mixture. We have the reactants in the perfect amounts. Neither is limiting. The molar ratio comparison is a fast way to check this. I know limiting reactants can feel tricky. The best way to get comfortable is to practice. Here are 2 problems for you. Pause the video and determine the limiting reactant for each. Question 1. Hydrogen gas reacts with chlorine gas to form hydrogen chloride. If you react 1.5 moles of hydrogen with 3.0 moles of chlorine, which is the limiting reactant? Question 2. If 46.0 grams of sodium reacts with 80.0 grams of chlorine, which is the limiting reactant? Ready for the answers? For question 1, the equation is already balanced. The molar ratio of H2 to Cl2 is 1:1. Since we have 1.5 moles of H2 and 3.0 moles of Cl2, there's clearly too much chlorine. So, hydrogen gas, H2, is the limiting reactant. So, hydrogen is the limiting reactant. For question 2, you first had to convert both masses to moles. You should have found 2.0 moles of Na and 1.13 moles of Cl2. The molar ratio from the equation is 2 moles of Na to 1 mole of Cl2. To react all 1.13 moles of Cl2, you'd need 2.26 moles of Na, but you only have 2 moles. So, sodium metal is the limiting reactant. The limiting reactant is sodium. You are now able to identify the limiting and excess reactants in a chemical reaction. And with that, we've covered the key concepts of stoichiometry. Let's do a quick final recap. Let's quickly review the major concepts we've covered today. First, we learned about the mole, which is the chemist's unit for counting particles. We learned that the molar mass, found on the periodic table, is the mass in grams of 1 mole of a substance. We also saw how to use the mole equation, N equals m/m, to convert between moles and mass. Then we moved on to stoichiometry, which is the art of performing calculations with chemical equations. The key to stoichiometry is converting everything to moles, using the coefficients in the balanced equation to form a molar ratio, and then converting out of moles to find the answer. And finally, we learned that the limiting reactant is the one that runs out first and determines the maximum amount of product, called the theoretical yield. I know this is a lot, but you have built an incredibly powerful foundation today. These concepts are the engine that drives so much of chemistry. My advice? Go back through these examples. Try the practice problems again without looking at the solutions. The more you do these calculations, the more intuitive they will become. You've got this. Keep practicing, and it will finally make sense. Thanks for watching.